How do I calculate the potential? Well, first of all, what do you expect the potential to look like? Right. On the outside, I have a constant electric field. So if I look at the system, here is my slab. And on the outside, electric field is constant. Now, means that if I put a charge Q here, I have to actually, to get closer to this slab, I have to keep pushing it. I have to keep pushing it towards the charge. Or if I let the system go, it's actually going to go to infinity. And does the electric field weaken as I go far away?
Yes.
Who said yes? No. Okay. Intuitively, of course, we all expect the electric field to get weaker as we go away from charges. But this is an infinite system. Okay? For an infinite system, there is no scale. I'm further away compared to what? Compared to infinity, which means I'm not further away at all. So the electric field does not weaken at all. What does that mean? What's the potential at infinity? Again, I have the same problem. The potential at infinity is infinite. All right? So, even without calculation, I can say I know that potential at infinity should go to infinity. When I look at a system, I can quickly ask, did I put charges at infinity? And in this problem, yes, obviously, I had a very broad thing, do it very fast. Okay, I had an infinite plane, so I actually put a lot of charges at infinity, which means I cannot blindly take the potential at infinity to be 0. So there are charges at infinity. So here's what I'll do. I'll choose the most symmetric point. You remember my coordinate system? Here's my coordinate system as a function of z. I'll choose v of z equals to 0 as 0. I can always choose the point, the potential of one point. Okay? And now I'm actually choosing that to be the most symmetric point. All right? Good. Then how do I calculate v as a function of z? Well, v at z minus v at 0 by my definition will be minus from 0 to z e of z prime dz prime, right? That's e dot dl. So clearly I have to be careful. I have to look at the potential inside and outside. Let's start with the inside now. What if z is less than d over 2? Now, v of 0 I took at 0, so v of z is going to be minus from 0 to z. Inside, my electric field magnitude was z rho over epsilon 0. So that's what I'll write. Z rho over epsilon 0 times dz. And I'm going to put primes here just to remind me that I'm doing my integral from 0 to z. This must be a different dummy variable. Okay? Now, what's this integral? Minus rho over epsilon 0 z square over 2. Good. How about if z is larger than d over 2? Now again I have the same E magnitude of z dz business from 0 to z. But now the functional dependence of the electric field is different on the inside and on the outside, right? What did my electric field look like? It was linear on the inside, but it was a constant on the outside. So I'll do the following. I will split this integral from 0 to d over 2 E of z dz, from d over 2 to z E of z prime dz prime. Okay? Any integral I can do that. I can integrate from a to b in two parts, from a to c and from c to a, right? I'm not doing something fancy here. Now, on the inside, what is the electric field? We just wrote it down. It's rho z over epsilon 0. And on the outside, what's the electric field? We found it. It was rho d over 2 divided by epsilon 0. Rho d over 2 epsilon 0. Okay, so this is going to give me minus rho over epsilon 0 z prime squared over 2 at 0 and d over 2 minus everything inside is a constant, rho d over 2 epsilon 0. So the integral is just z, or z prime if you want, from z to d over 2. So minus rho over epsilon 0 d square over 8 minus rho d over 2 epsilon 0 z minus d over 2. Let me write everything nicely. This is going to be minus rho d square over 8 epsilon 0 plus rho d square over 4 epsilon 0 minus rho d over 2 epsilon 0 z, or plus rho d square over 8 epsilon 0 minus rho d over 2 epsilon 0 z. So what does this potential look like? Let me write them separately. V of z is minus rho over epsilon 0 z square over 2 when z is less than d over 2, and it's rho d square over 8 epsilon 0 minus rho d over 2 epsilon 0 z when z is larger than d over 2. What does it look like? First of all, what is the point with the greatest amount of potential here? Let's think about it. If I actually take a charge from infinity I'm going up the hill. I'm going opposite to the electric field. Where is my peak? Where is the point with the highest potential? No. Even inside the surface, I have an electric field that's opposing it. Right? So it's not the surface. If I go to the midpoint, I will actually reach a point of higher potential. Okay? In other words, I chose potential. So let me shift my axis a little bit. I chose the potential at the maximum point to be 0. So all my potentials are going to be negative. That's okay. So on the inside, what does the potential look like? It actually decays as z square. Then what's the value at d over 2? It's going to be rho over epsilon 0, d square over 8 minus. And then from that point on, it's going to go linearly down to infinity. Okay? So it's kind of interesting. And the potential on the other side for negative z will be just the symmetric. So, okay, that's going to be true for, and this is not r, this is z, right? So on the inside, I have linear electric field, which means I have a parabolic potential. And on the outside, I have a linear potential, which means I have constant electric field. Right? Good. So one thing we actually learned about the potential is to calculate it from the electric field, and that's when electric field is actually easy to calculate by Gauss's law. We've also done one more thing. We've actually done examples where it's actually easier to calculate the potential and then find the electric field. Okay? And let's do an example like that. Right? Any questions on this problem? Do you feel confident that you can actually use electric field to find the potential? It's just integration. The worst thing that can happen, and it will happen frequently, is that you mess up the sign. So whenever you find the result, please think about the sign. Am I going against the electric field or in the direction of the electric field? Any questions? No? Good. So let's solve another example. And this time I actually want to go away from integration a little bit. Okay. I want to do something else. Let me remind you a problem we have solved previously. We have actually solved the following problem. If I have two charges, q and minus q, which are separated by a distance d, we found the electric field on axis, right? What was this arrangement called? It was called a dipole, right? And it's and do you remember why it actually gets a special name? Why is this important? Because a lot of systems, when you think of them, although they can be neutral, like the hydrogen atom, where there is an electron and a proton, okay, the net charge, the total charge is 0. Does that mean that there will be no electric field away from the system? Not unless these two charges are exactly on top of each other, and they will never be exactly on top of each other. There will be a small distance. So when the distance is small, we actually want to understand what kind of electric field we see from such a dipole system, right? Previously, we only calculated this electric field on the axis of the dipole. Now what I would like to find out is, what does the electric field look like perpendicular to that axis? What is the electric field perpendicular to the axis of the dipole? I'm going to use the board again. Good thing I have. So here's the question once again. Let's say this is x, this is y. I have a plus q charge and a minus q charge. This is a distance of d over 2 from the origin. The other is also d over 2 from the origin. I actually would like to find out if I'm very far away, a distance r away from the center of this dipole, I would like to find the direction and the magnitude of the electric field. Let me give you not only r, but also the angle theta. And clearly, you see the problem and you think, hey, Özgür Hoca is not in his element today. He is supposed to be talking about the potential. Instead, he is asking us to find the electric field. I actually am doing this on purpose because it turns out this problem is easier to solve using the potential. So if we first find the potential and then find the electric field, things are going to be quite easy. And I'm going to do this by assuming the distance from the dipole to my observation point is much, much larger than the distance between the charges. So think of this atom, and I'm looking at the atom from afar. Right? So how do I do this? I'll do the following. I'll actually say, hey, let me first calculate the potential created by these charges. Can I do that? Yes. So x will be r cosine theta, y will be r sine theta, now what is the potential created by the plus charge? And I don't have another color here, so let me call this r plus and this r minus. This is going to be potential created by the plus charge plus potential created by the minus charge. Plus charge potential will be q over 4 pi epsilon 0 r plus. Potential created by the minus charge will be minus q 4 pi epsilon 0 r minus. What is r plus and r minus? R plus is going to be square root of x squared plus y minus d over 2 squared. And r minus will be square root of x squared plus y plus d over 2 squared. Right? So it all looks really simple. Q over 4 pi epsilon 0, 1 over r plus plus minus 1 over r minus. Now, here is the thing though. I don't really want the full expression. The problem specifically asks me to consider r being much, much larger than d. So let me expand both of these things. Now, r plus is square root of x square plus y square minus yd plus d square over 4. R minus would be the same thing with a plus sign here. Now, x square plus y square is r square is x square plus y square. So, if I take r square out, I'm going to say this is r times square root of 1 minus plus y d over r square plus d square over 4 r square. Now, d over r. If r is much larger than d, d over r is much smaller than 1. How about d square over r square? Say d over r is a number like 0.0001. D square over r square is much smaller. So this is actually going to be much smaller. Which means I am going to make my first approximation. I'm going to neglect it with respect to yd over r square or 1. So this is going to be the smallest term here. So this is actually important. I don't care in which department you are. You should be listening right now, because all of us, scientists, engineers, we always solve problems approximately. It's very rarely that we'll actually solve our problems exactly. So, I can do further approximations. Do you remember what 1 plus x to the n approximately was equal to if x was much less than 1? It was 1 plus nx. So I'm going to say yd over r square is very small. So this r plus minus is r times approximately 1 minus plus square root is power to 1 over 2 y d over r square. Furthermore, I'll do the following. I don't need r plus and r minus. I need 1 over r plus or 1 over r minus. Then 1 over r plus is approximately 1 over r times this whole thing to the minus 1 power. But I already used the approximation once, 1 plus x to the n. So what is 1 over 1 plus x? It's 1 plus x to the minus 1 power. So this should be almost equal to 1 minus x. It may look weird if you're doing it for the first time. Believe me, it's not. Just put x equals 0.001 on your calculator, punch the numbers a few times, and you'll believe I'm not doing something crazy. So this is 1 over r times 1 plus 1 over 2 y d over r square. So, how about the minus? It's going to change the sign. So now I can approximately write what the potential is. Q over 4 pi epsilon 0. 1 over r plus is 1 over r, which is going to be there for everything. 1 plus 1 over 2 y d over r square. 1 over r minus is going to be minus 1 minus minus plus 1 over y d over r square. Overall, now I can maybe clean all this up. And if I fix my computer, I will actually try to put these into lecture notes, so don't panic. Now I have a nice formula for v of x, y. It's going to be q over 4 pi epsilon 0 r. The first terms cancel. The second terms just add up. Y d over r square. Or if I write this all up, q d over 4 pi epsilon 0 y over r cubed. But that was not what was asked. I need to find the direction and the magnitude of the electric field. Or if you want, the electric field as a vector. So how do I do that? First, let me write everything in terms of x and y. Y is already there, but r is square root of x squared plus y squared to the third power. How do I find the electric field? Electric field is going to be Ex I hat plus Ey j hat. What is Ex? Ex is, what was our formula? Partial derivative of the potential with respect to x with a minus sign. So let's do that. Let's take the partial derivative of q dy divided by 4 pi epsilon 0 x squared plus y squared to the 3/2. What was the meaning of partial derivative? X is the variable, anything else is a constant. I don't care about that. Let me take the constants out. dq y over 4 pi epsilon 0. The derivative with respect to x with a minus sign of 1 over x squared plus y squared to the 3/2 minus dq y 4 pi epsilon 0. This is to the minus 3/2 power. On the inside I have x squared, which is going to be, give me 2x, divided by the whole thing to the 5/2 power. Let's do the cancellations. So this is going to give me q times d divided by 4 pi epsilon 0 x y divided by x squared plus y squared to the 5/2. I'll do the y integral in a moment. But let me, well, not integral, I'm sorry, y derivative in a moment. But let me check. What do I expect the electric field, the x component of the electric field, to be when x is equal to 0? When x is equal to 0, the electric field on this point should be in the y direction, right? So when I put x equals to 0, I expect this formula to give me 0. Does it give me 0? Yes. How about if I'm on the x-axis? If I'm at some point here. What's the x component of the electric field? Let's think. The negative charge will give me an electric field like this. right? The positive charge will give me an electric field like this. So the x components would cancel each other. So when y is equal to 0, when I'm on the x-axis, electric field, the x component of the electric field should again be 0. Do I find it to be 0? Yes, I do. Question?
Why on the y-axis the electric field should be 0?
Not the electric field, but the x component of the electric field. Good question. Let's quickly find the y component. Let me take a derivative with respect to y also. And for that, I will just replace this whole thing with the answer dq over 4 pi epsilon 0 xy divided by x squared plus y squared to the 5/2. And here, now I have to be more careful. I have minus q d over 4 pi epsilon 0 del by del y y divided by x squared plus y squared to the 3/2. Minus the constants. Now, derivative of the numerator is 1. So the denominator is x squared plus y squared to the 3/2 minus y times derivative of the denominator, which is 3/2 2x x squared plus 2y, excellent, 2y times x squared plus y squared to 1/2 divided by square of the denominator, x squared plus y squared to the 3rd power. Let's play around with it. Maybe I can take a power of 1/3 out of this, or 1/2 out of this. So I'm going to say minus dq over 4 pi epsilon 0. Then I'll have x squared plus y squared minus 3y squared divided by x squared plus y squared to the 3 minus 1/2 is 5/2. So now I can probably just write the result. Ey is minus dq over 4 pi epsilon 0 x squared minus 2y squared divided by x squared plus y squared to the 5/2. Okay. Now, okay, the expressions look a little bit nasty. And it looks even nastier because my computer broke down. But that's supposed to be a joke, guys. Come on. Try to show an effort to love. Now, the thing is, try doing the same calculation with the electric field. First, write the electric field components, and then try to do the approximations. It will be horrible. There is no way I'll be able to do that just on a single piece of blackboard. Okay. So, what did potential actually help me do here? It was easy to write the first expression for the potential and do the approximations there. Taking the derivatives actually allowed me to find the electric field in an easier way. So, right now we're going to end this with a quiz, and this is exactly what you need to do. It's easy to calculate the potential in the quiz, and the next lecture will start by solving that quiz. Okay? Is there a question? No? Okay.